Hello everyone. The title of the work I'm going to report today is Codebook Knowledge with Mamba-Transformer for Low-Light Image Enhancement. The report will include background, motivation, specific methods, implementation details, and experimental results. Let's get started. There are several background factors for enhancing low-light images. First, most deep learning methods don't factor in all the different types of degradation that overlap and interweave with each other, and that limits how well they can handle all the various complex low-light scenarios in the real world. For example, some mostly focused on fixing color distortion, while others only concentrated on adjusting illumination. Their narrow focus usually led to less than ideal performance. So one of the main challenges with low-light image enhancement is basically closing the domain gap with the ground truth across all different sorts of degradation scenarios. Second, most VQ game-based methods for low-level vision run into this issue. When they are processing highly degraded inputs, the features they extract often have a big domain gap with the high-quality image pairs. So the codebook is basically a knowledge base that is learned from the high-quality image domain. How to effectively map the features from the low-quality domain over to this high-quality one for retrieval is also a domain adaptation problem. Third, the textures in the high-quality features we retrieve from the codebook might be compromised, because nearest neighbor matching processes each feature factor on its own at every pixel and totally overlooks the structural information. So, we proposed a novel method called CodeEmptyNet to solve aforementioned challenges across diverse degradations. Stage 1. We pre-train a quantized autoencoder to learn the codebook that is packed with textual knowledge and fine details to avoid the limitations that not considering all the degradation types. Stage 2. We have designed a domain adaptation encoder called DAE with implicit neural representation regularization and hybrid Mamba-Transformer module called MCRB to predict high-quality token features and adjust domain distribution. Stage 3. We focus on training a lightweight controllable feature fusion module. The module called CFF with an adjustable parameter can provide flexible balance between restoration, quality, and fidelity. The details of DAE, MCRB, and CFF can be shown here. DAE is based on several NRL and ResNet block, while ResNet block aimed at feature extraction, and NRL learn the global illumination to enable gradual features distribution adjustment. NRL use implicit neural representation method called NRN to recover high-frequency details and information. We delve into the characteristic of NRL and using NRN to process two images with different light intensities. The distribution of Y-channel pixel values is similar, and a heat map of their brightness differences show a low value. It can be seen that the NRN method has the ability to learn universal illumination. We plan to utilize this characteristic to enhance low-light images. Given features FL extracted from low-quality images, high-frequency function maps its pixel coordinates to a high-dimensional space and low-quality features concatenated high-dimensional pixel information to generate FL2. Then FL3 is got via multilayer perceptron and concatenated with original FL in channel-wise direction. A lightweight 3-layer convolutional network is employed to obtain a context-aware illumination estimation and get final output via residual connection. MCRB is a hybrid Mamba-Transformer architecture with 6 Mamba blocks and 2 Transformer blocks, while VSSM is the core of Mamba block. The MCRB helps explore complex nonlinear evolution of feature distribution and avoid inaccuracies in predicting code indices that could lead to failures in the nearest neighbor matching algorithm. CFF modules processing can be shown as the equation. Alpha and beta are several lightweight convolution blocks, while W is a controllable parameters for feature fusion. 3 public datasets results are shown at here. We compared our method with many state-of-the-art methods in recent years on 3 public datasets. 3 public available datasets are called LLL version 1 dataset, LLL version 2 real dataset, and LLL version 2 synthetic dataset. On all the 3 datasets, CodeMTNet significantly outperformed NURCO, which also employed implicit neural representation regularization. On LLL version 1 dataset, CodeMTNet has achieved approximately 0.5 dB higher peak signal-to-noise ratio than CodeEnhance, which is another codebook-based low-light image enhancement method. The learned perceptual image patch similarity scores achieved by CodeMTNet outperforms all state-of-the-art methods on all 3 datasets. It indicates that the restoration results by CodeMTNet are more in line with the people perception, demonstrating the effectiveness of our approach. We conducted a considerable number of ablation experiments, not only analyzing the effectiveness of the module, but also delving into the parameters of NL and the potential architecture of MCRB. Table 5 demonstrated that 6 Mamba block and 2 transformer blocks is the best plan. Simple Mamba and transformer architecture is less than ideal performance. The ablation also showed that simply stacking transformer blocks and Mamba blocks is not as effective as using an appropriate ratio. Finally, we also compared our method with several state-of-the-art methods in terms of generalization. We randomly selected 3,000 of these paired images for generalization test on CodeMTNet and some state-of-the-art methods, which are respectively evaluated on 4 common metrics using weight trend on LL version 1. The experiments show that our method has excellent performance in complex street environments. We conducted a comparison of codebook-based and non-codebook-based method on LLL version 1 dataset. Compared to other low-light image enhancement methods based on codebooks, CodeMTNet has lower complexity while maintaining superior generalization. However, methods based on codebooks are still plagued by their high complexity, and future work is expected to address this issue. For conclusion, we propose an effective codebook-based low-light image enhancement method to tackle multifaceted and intertwined degradations typically encountered in low-light scenarios. We reconsidered the application of vector quantized codebook in low-light image enhancement task as domain adaptation paradigm, and designed 2 key modules to solve domain adaptation problem. Finally, through comparison on public datasets as well as testing and applications, we demonstrate that CodeMTNet has not only competitive performance but also strong generalizability compared to many state-of-the-art methods. Thanks for listening.